Welcome back. In this lecture, we will look at how the positive charge of the nucleus affects beta decay. So the main results from experiments are the following. Beta minus decay and beta plus decay differ in certain features and they have certain common features. At higher energy, the number of beta particles, whether it's beta plus or beta minus, is less. And in the previous lecture on the statistical factor um, in within the Fermi theory of beta decay, we were able to explain why this is so. But however, you would see that the number of particles with higher energy is more in the case of beta plus decay compared to beta minus decay. And the other feature that is different is that uh, the number of particles at very less energy, that's a lot more in the case of beta minus decay compared to beta plus decay. The one common feature of it being a continuous distribution uh, is common to either beta minus or beta plus decay, and that has been explained in the previous lecture. So let's try to look at this qualitatively without deriving it from first principles. From mathematically, we will not derive this, but we will try to argue from some physical grounds. So beta minus is a negatively charged particle. And because nucleus is positively charged, there is a strong attractive interaction between the beta minus particle and the nucleus. So when beta minus particle is moving away from the nucleus, it has to do work against the attractive interaction. Therefore, it would tend to lose kinetic energy. So the beta minus particles are slowed down in general. So there are a lot more particles which have very low energies. Okay, so the general argument is that the attractive interaction between the beta minus particle and the nucleus is the reason. Okay, so when you try to move against the attractive interaction, you're doing some work, and which makes the beta minus particle lose energies. Therefore, the number of particles at low energy increases. In contrast to this, when you have beta plus particle, this is because they are positively charged, there is repulsive interaction between the positively charged nucleus and the beta plus particles. Therefore, their kinetic energy is increased, okay, in a way that they are thrown out of the nucleus because of this repulsive interaction. Therefore, in general, the energy also increases, as you can see, the kinetic energy, the maximum kinetic energy of beta plus particle is larger compared to beta minus decay. In addition, you have larger number of particles at somewhere higher energies, okay, somewhere in this region, okay, in the case of beta plus decay, okay. So there is a strong repulsive interaction between beta plus and nucleus, strong attractive interaction between beta minus and nucleus. This is the main reason behind this kind of distribution, which is different for beta plus and beta minus. Okay, so this can be derived mathematically, and you get some such expression. This is called the Fermi factor, which depends on the atomic number as well as the energy of the beta particle. We will not derive this. We're just going to use this expression. And these factors involve the atomic number. This is the speed of beta particle, that is velocity divided by c, right? So this beta refers to normalized velocities. Okay, so we have defined this in some previous lecture. So this is a non-dimensional energy. This is a non-dimensional momentum. Okay, and alpha also has other important fundamental constants. Okay, so this is a fine structure constant is something which you would see in many aspects of physics. So, okay, so with this expression, you can rationalize this behavior, the difference between beta plus decay and beta minus decay. There are a few other additional aspects of Coulomb interaction. Outside the nucleus are the electrons, right? So they are negatively charged. The atomic electrons, that is outside of the nucleus, they have a repulsive interaction between beta minus particles and the electrons, right? They're, after all, electrons, they are two or electrons. Therefore, the number of beta particles that are coming out of the nucleus, beta minus particle, decreases because of the electrons, atomic electrons that are outside the nucleus. So there is number decreases by 2% for atomic number approximately 50. And if you have higher atomic number, the decrease in number of beta minus particle is even larger. As you would expect, that the trends would be opposite for beta plus emission, because the beta plus emission, you have a positive particle that is emitted out of the nucleus. So the negatively charged electrons will pull those particles out. So there increases the number of beta particles coming out of the nucleus increases by about 30%, 35, 37% for atomic number 50. And if the nucleus has greater atomic number, the number of beta plus particle also increases. So even though the rest mass of beta minus and beta plus are one and the same in terms of emission, the rest mass is the same. Therefore, the energy of beta plus and beta minus is, from the point of mass, is the same. The nature of beta plus emission is different from beta minus emission, mainly because of Coulomb factors, interaction with the nucleus and interaction with atomic electrons outside the nucleus. In the next lecture, we'll briefly touch upon other feature of beta decay that is relevant to rationalizing half-lives of beta decay. We'll take that up in the next class. Thank you.